In this video, I'm going to discuss restriction enzymes, and these are types of molecular scissors in our cells. So a restriction enzyme is a specific endonuclease that can cut double-stranded DNA. In other words, it can cut both backbones of the DNA. And how they do this is by recognizing short sequences of DNA called recognition sequences. And then they'll cleave the DNA at or near that recognition sequence. So a typical recognition sequence we see discussed often is of the restriction enzyme EcoR1. So EcoR1 will cut at a specific restriction sequence, namely GAATTC. And what happens then is that there is the creation of what we call sticky ends on each side then of that cut. We'll then need a glue, a type of glue, of course, in the form of a molecular enzyme, namely ligase, then to glue these sticky ends together when we join those DNA fragments together again. So if we know that this type of restriction enzyme cuts at a specific sequence, we can find useful applications for this in many instances. So just to also clarify something here, the bonds that are broken when these restriction enzymes like EcoR1 cut are the covalent phosphodiester bonds within the backbone, and also the hydrogen bonds that are here in between the strands, between the individual nucleotides, the A's, the T's, the C's, and the G's. Now, originally, this type of enzyme, a restriction enzyme, was found in bacteria, and they seem to use this as a type of natural defense mechanism to cut foreign pieces of DNA. But now we, of course, can clone these. They're commercially available. For example, if we want to do some experiments with EcoR1 in the laboratory, we can order some EcoR1 and then we can do experiments with those. Some of these restriction enzymes do leave blunt ends and others do staggered cuts. In other words, they can do a single-stranded cut with a 5' overhang or a 3' overhang. And this is what happens in the case of EcoR1. It creates those sticky ends. So this would be a sticky end over here, and then this would be a sticky end over here. And you can join these ends up by having that ligase enzyme available to glue them back together. So it's important for molecular biologists to create these unpaired sticky ends, and then they can anneal or glue them back together with any complementary sequence in a different organism's DNA. Now today we know of more than 3,000 types of restriction enzymes. I do want to show you how we read a restriction map. Let me open this one for us. This is an example of a restriction map for the plasmid PGEN101. Its total length is 20 kb. Let me just remind you that a plasmid is a circular piece of DNA, right? It is often found in bacteria, and so this plasmid, of course, can differ in size, right? You can have a small plasmid, you can have larger plasmids, and we can measure their length by measuring, their perimeter. How long are they? Now, in the case of using a map as a guide, we're asking you in this example to follow along and give the number of restriction fragments along with their associated lengths. Give the number of restriction fragments along with their associated lengths that would result from digesting this plasmid with the restriction enzymes EcoR1, BAM-HL, and also a combination of BAM-HL. So what we'll have to do here is look at what kb length we'll end up with if we only have EcoR1 present, what kb length we will end up, or maybe multiple lengths will end up if we have only BAM HL, and then if what will we get if both of them are present there in the plasmid mixture. Okay, so let's do this. Let's look at echo R1 first. I think I'll use some different colors here to highlight that for you so that you can see that better. So here, of course, is echo R1. I'm going to use the purple to show you if we measure the length of the plasmid from here, the starting point, all along the perimeter, we see that we have a 8 kb plus 6 kb over there, plus 2 kb over here, plus 4 kb over there. So that gives us a total of, you count with me, 20 kb, right? 6 plus 6 is 12, plus 8 is 20 kb. So we're literally looking at the different lengths of these cuts created here for us, you know, as a guide, but we're adding all of those together. So what I'm saying is the total circumference here of the plasmid, right, is what is 20 kb. So if you only have echo R1 there, then what will happen, let's erase all of this, is that echo R1 will come in over here and it will cut. And then if you could imagine, it creates now a long piece, right? A long piece of this plasmid. So you're opening up this circle, and the total length, you know, of this is 20 kb. All right. So next up, let's look at BAM HL. What do we see here that the BAM restriction enzyme can create? Well, we see that if we put it in there, we can have a 2 kb. We see that we can have a 6 kb, and we see that we can have also a 12 kb, right? So we're ignoring. So let me draw a little line over this so that helps. So we're ignoring echo R1 here, and we're seeing that BAM HL can be also a longer, you know, fragment here. So we could have a 12. So let's summarize that. We see a 2, we see a 6, and we see a 12. Okay, now what would happen if we add both of these restriction enzymes in the mix, both echo R1 plus the BAM restriction enzyme? So let's clear all of this out so that we see. And so we now have to consider that the echo R1 is present, and it is going to cut here, right? And we need to consider that the BAM is present and it will cut there and there and there. So now we end up with 4 fragments, and those 4 fragments, the smallest one is the 2 over here, 2 kb, and then we have a 4 on this side, and there is a 6 over there, kb, and lastly we have a longer one, an 8 kb. So it really is quite simple in how we read a plasmid and how it is cut by restriction enzymes. Of course, you can add many together, and then it makes it a little bit more complicated. But I think the easiest way to start to look at this would be to look at what does it look like if you have just the one restriction enzyme present, and then you compare it with the other one, and then what does it look like if you consider all of them together.